Okay, 7e. So find the residue of each function at 0. Okay, if you put a 0 in, you get a 0 in the numerator. Okay, 0 of multiplicity 1 in the numerator. And then down here you get a 0. This is a 0 of multiplicity 2. So that means that what we have here is a pole of order 1. Okay, because 2 minus 1 is 1. Okay, so that's how I come about that. So sine is generally going to give you poles of order 1, but sine squared is going to be 2 because it's squared. And then the same thing up here, e to the exponential of 4z. You can see this by the Taylor series expansion. So exp of 4z, that's like 1 plus 4z over 1 factorial plus 4z squared over 2 factorial plus 4z cubed over 3 factorial. So if you take and subtract 1 from this, you take that 1 out, then you're going to have a 0 of order 1 at 0. Okay, so that's a 0 of multiplicity 1. This is a 0 of multiplicity 2 down here. So that gives us a pole of order 1. So now the residue, what we can do for the residue is we know that it's going to lead off with this term. Like that. So we know that there's going to be a Laurent series involving powers of z that it will start right here. This is a polar order 1, so this will be the first term. Okay, that being a polar order 1 means that's going to be the first term. Okay, so the objective is to find this c minus 1, because that's the residue right there. So that's the objective. Find this, and we're done. Okay, so in other words, this is the residue. Okay, so the way to do that would be you can multiply both sides by z. And then you'll have this, you'll have a Taylor series. And then take the limit as z goes to 0, and that's going to be your c minus 1. Okay, so you just need to find that limit. And I suppose there's a couple of ways you can do that. You can use L'Hopital's rule, but I'm going to show you a different way. Okay, so up e to the 4z minus 1. So e to the 4z has this expansion, right? E to the 4z minus 1 has this expansion here. So multiply that by z. And you'll have 4z plus 4z squared over 2 factorial, and so on. That's going to be the numerator. Now the denominator is a couple of sine z's, and you know that sine z is z minus z cubed over 3 factorial plus so on, right? And then you're doing that twice, so z minus z cubed over 3 factorial and so on. Okay, now if you factor a z out of the numerator, you get z squared, right? And you have 4 plus And this will be 16z over 2 factorial. Then the other stuff's gonna have z's in it. Okay. If you factor a z squared out of here, then you're gonna have 1 minus z squared. So you factor a z out of here, and you factor a z out of here, and that's factoring the z squared out, right? And then these z squareds will cancel, and you just end up with, when you plug, then you can plug zero in for z. Everything, all this goes away, all these goes away. You have 4 over 1 times 1, so that's just going to be 4 over 1 times 1. That's going to be 4. Okay, so that's another way to do it. But the normal way, probably from a calculus point of view, after taking calculus, the way that you would find this would be L'Hopital's rule. But this is another way to do it. So it should be, answer should be 4. Okay?
Okay.
Great. Any other questions? Okay, if not, we'll continue on where we left off last time. And I want to find some space. Okay, here's what we're going to do. I want to construct a function, and here's what it will be. Okay, so I'm going to call it f of z. And first of all, I want it to have a couple of different, I want to have be 0 at a couple of different points. So the first point we'll call z naught. And we want to put a power up here. Do you guys want to choose a number between that's 2 or more? Does somebody want to choose who wants to choose some numbers for me?
4.
Okay, 4. Okay, then give me another number that's 2 or more.
5.
5. Okay. And then another number. Even bigger. Go big if you want. Doesn't matter. Doesn't really matter.
11.
11. Okay. Good. That's fine. I'm going to make this 50 because I don't want them to be consecutive. Okay. So, and then I have this other thing. Okay. So let's suppose, and what we're going to say is we're going to say that H is, what we're going to say is H is holomorphic or analytic, and H of Z is not 0 inside gamma. Okay, and also I'm going to say here's Z0, here's Z1, and here's Z2, and I'm going to say that's gamma. Okay, so positively oriented curve. Positively oriented simple closed curve. Okay, and then there's these 3 points inside. So this is like, the Z2 is like, this is a pole, right, inside here. And H of Z is holomorphic, so Z2 is the only pole that's inside. Okay. Okay, so, but what I want you to do is consider this. F prime of Z over F of Z. Consider that quotient. I'll figure out what that is. Now, this piece right here, I can put that as, I can put it up in the numerator as -11, because I want to take the derivative, right? So I'm going to put that up there as as z minus z2 to the -11. Okay. Okay, so what's the derivative of all this? Well, it's a big product rule. You got one, two, three, you got 4 products, right? Basically, because I put this up here, it's a product. So it's the derivative of the first one times the rest, okay? Plus the derivative of the second one times the rest. Times the rest of the other, I mean by rest I mean the other terms. Plus the derivative of this, we'll go this one. We'll go this one next. Oh no, the derivative of this one. So h prime of z times the rest plus, and then the other one's gonna be minus 11 z minus z2 to the 10th, to the -10th. No, not 10. I can't do subtraction, 11. Okay, so subtract 1 from there, you get -11 times the rest of the stuff. And that's all going to be divided by z minus, by f. And h, and okay, so if we take, so let's look at this piece right here. If we divide this by this, what do we get? All this divided by this. And by the rest, I mean, remember this term, this has this term, that term, and that term in it, right there. And so they're going to cancel with these 3, right? And then this divided by that is going to give you what?
Four
That's going to
over z minus z naught.
Z minus Z naught, right? Okay, now, choose a different color here. Now let's go with this one. What's that going to give you? When I take this and divide it by all that.
50 over z minus z naught.
Z minus Z1, right?
Oh yeah.
And then I get this one. That's going to be h prime of z over h of z, whatever that is. And then finally, I have minus, and this one right here, so this over that, wait, this over this is actually going to be 11 over z minus z2. Okay? So, okay, so where am I going with this? Well, let's suppose that we want to find the integral around this curve of f prime of z over f of z. Well, according to what we just did, we know that it's 4 over z minus z naught plus 50 over z minus z1 plus h prime of z over z minus 11 over z minus z2. Okay, now what is this integral going to be? The integral, so ignore all these and just look at this one. What's this integral going to be? Here's the naught right here, right? Here's the naught right there. So what's this integral going to be? If you just integrate just this piece, what are you going to get? Just that piece.
Is it 2 pi I?
Yes, 2 pi I times 4, right? Because you have a 4 in the up here. So if it was just a 1 over that, then it would be just 2 pi I. Okay, and this one's going to give you, integrate that piece. Oops. Well, integrate this piece, you're going to get 50. Now I said that H is holomorphic and it's not 0. So that means that its derivative is holomorphic and this is not 0. So that means this is holomorphic. So that's gonna be 0, right? And then this last piece is going to be minus 11. So we can do the math, but we can just do the arithmetic to get this. It's going to be 2 pi I times these numbers right here, right? That plus that minus that. Okay, but these numbers, what's the relationship between these numbers and the original? Well, there's the 4, there's the 50, and there's 11. So 4, 50, and so it's 2 pi I times this one plus that one minus that one. So the multiplicity of the zeros added together minus the multiplicity of the poles. Okay, so if we had another, so it's, we can also think of it as the number, we can simply say this is the number of zeros minus the number of poles. Okay, so the number of zeros counting multiplicity, which is 54, minus the number of poles counting multiplicity, so that's minus 11. Okay? And that is the argument principle. Okay, so this is theorem 917. Okay, so we just kind of showed how that works. So this is, except here they have 1 over 2 pi I in the integral of f prime over f is equal to the number of zeros minus the number of poles. Okay, so suppose f is meromorphic and gamma, so that means homomorphic except for poles. And gamma is positively oriented, so on, and doesn't pass through any 0 pole, and that blah, blah, blah. And then, do you know Z as the number of poles, the zeros, and P is the number of poles counting order, then this is that. Okay, so that's exactly what we did. So they do it a little bit differently. So they take f prime of z over f of z. You get these values here, plus g prime of z over z, or over g of z, which we got h prime of z over h of z. And now it's going to give you 0. Okay. Okay, so that's how that works. That's called the argument principle. There's an exercise that deals with this. It's number 20 right here. So basically for this one, you have zeros and poles. Your zeros are Z1 through Zj, and your poles are P1 through Pk. So this number 20 is sort of doing the same thing that we just did. They're really similar to what we just did. So F is meromorphic, G is holomorphic, gamma is a positively oriented, simple closed piecewise path, and so on. The zeros and poles are these. These are the zeros, these are the poles. So that means that you're going to have, you have this G here also, that's the only problem. So let me just give you an indication of how you would do this, okay? So F of C is going to be, you have all these zeros, right? Z1, so Z minus Z1. Okay, and then you've got, and then it goes all the way to Z minus ZJ, right there. And in the denominator, you've got Z minus P1, and that goes all the way to Z minus PK. Okay, like that. And then you also have an H of Z. Okay, so F is meromorphic. That means it could be that. And then I said, and then H is like, just like what I said, another problem. So then you calculate this right here. Okay, and that you should get a similar thing to what we got before. And then, but here you're multiplying by that. Okay, so you have to take that into consideration. Okay, so that can help you with number 20. And let's move on. And we move to Boucher's theorem. Okay, so suppose F and G are holomorphic in a region G and gamma is positively oriented, simple, closed, piecewise, smooth path. And modulus of F is greater than modulus of G for all Z and gamma. Then the number of zeros enclosed of F plus G enclosed by gamma is equal to the number of zeros enclosed by gamma of F. Okay, so basically F dominates G on the boundary. That's what you're looking for. F to dominate G on the boundary. Okay, so let me give you an indication of how you can do this problem, how you can apply this, okay? I guess I should just do it right here. Okay, so let's consider this function right here. Z to the 7th minus 5, Z cubed minus 12. Okay, and I'm going to show that this has no zeros inside the disk of radius 1. Okay. Now, the idea is that you want to choose, you want to choose a part of this, that will dominate the other part. So you want to split this up into an F plus G. Okay, so you want to split it up into F plus G. And you want to choose F, so it dominates G on when the modulus of Z is 1. Okay, so that's because you want the modulus of F to be greater than the modulus of G when you're on the boundary, Z equals 1. Okay, because this right here is the circle of this inside. This is the disk. Okay, this is the disk, including inside. But you want just the boundary. You want F to dominate G on the boundary. Okay, so if the modulus of Z is 1, then the modulus of, so what you can think of, so maybe the way you can think about it is if we take the modulus of Z to the 7th Okay, so if modulus of z is 1, then modulus, and then this is going to be what? If I take the modulus of this part.
One.
Yeah, that's just going to be 1. What would the modulus of this be?
Five.
That's going to be 5. And the modulus of this one?
12.
12. Okay, and then 12 is more than the sum of those two, right? 12 is more than the sum of those two. So what I'm gonna do is I'm gonna choose f of z to be the one that dominates the other ones, negative 12. F of g to be that part. And then I'm gonna choose g of z to be the rest. Okay, so so the modulus of f is 12. The modulus of g, well, that's the modulus of z to the 7th minus 5z to the 3rd. So that's going to be less than or equal to the sum of the two moduluses, right? That's going to be less than 6. So modulus of, so that means that the modulus of f is greater than the modulus of g on the circle. Okay, so by Richet's theorem, the number of zeros of f plus g, okay, so now notice that that this is f plus g now. So f plus g, so this is f, this is g. Okay, so we've chosen this is f, and this is g. So f plus g is z to the 7th minus 5, z cubed minus 12. That's going to be equal to the number of zeros of negative 12. Okay, now how many zeros does negative 12 have? Well, it's never 0, right? It's always negative 12, so it can never be 0, so that's just going to be 0. So this has no zeros in there, no zeros in here. Okay, so that's an example of Richet's theorem. Now I'm going to use another example. I'm going to use it, show you another example, but I'm going to use the same polynomial. So the same thing, the same one. And I'm going to say this has 7 zeros in here. Okay? This has 7 zeros in here. So we already know that it has no zeros in the modulus of z less than 1. So to show this, all we really need to do is show that. Okay? We just need to show that. And then we'll have shown, so this is okay, so there's 7 zeros in here. 7 whatever. 7 zeros in here somewhere. Ooh. It's like one of those pastries. All of this, there's 7 sprinkles, there's 7 surprises in this part and no surprises in the middle. Okay. I don't know if I like that. It's green though. Okay. So, what you're looking at is you want to choose f and g. So you want f of z to be greater than g of z on the boundary. Now this time the boundary is modulus z equals 2. Okay, so what's this modulus going to be? If modulus of z is 2, then modulus of z to the 7th.
It's 2 to the 7, 128.
Yes. Well, that's 128. That's pretty big. Okay, and this one right here is going to be
40.
That's going to be 40. So 5 times 8, 2 to the third is 8, and this is going to be 12, right? Okay, so this is the larger one, and it's also bigger than both of these combined. So you want it to be bigger than both those combined. So we're going to choose f of z to be z to the 7th. We're going to choose g of z to be the rest of it, which is negative 5 z cubed minus 12. Okay, so modulus of f of z is greater than the modulus of g of z on when the modulus of z is 2 on the boundary, on this boundary here. So that means the number of zeros of the sum, which is z to the 7th minus 5z cubed minus 12 in this disk is equal to the number of zeros of z to the 7th in this disk. Okay, so now how many zeros does z to the 7th have in here? If I form a new function, so if I said f of z equals z to the 7th has how many zeros in modulus of z less than 2? Well, it's only 0 right here, right? At the origin, because that's where you plug 0 and you get 0. But this counts as 7 zeros, right? Because it's multiplicity 7. So that counts as 7 zeros. Okay, so that's 7. It has 7 zeros. So this polynomial has 7 zeros in the green region. Well, it has 7 zeros inside here. We know it has no zeros in the blue region because of this. So those 7 zeros have to be in here in the green region, which is that. And
So you said that the origin is one of the 0, but all 7 zeros are in the green part?
no, this F part, just this part has 7 zeros at the origin. Just that part. That's your F. That has 7 zeros at the origin. The whole thing has 7 zeros in the, this whole thing has 7 zeros in the green part.
Okay.
Okay, but